So our next speakers are Esther Needham, who's a transportation planner at Nygaard Consulting Associates, working out of Portland, and Bryan Blanc, who's a transportation planner, data scientist. They're talking about using shiny dashboards to understand bus transit delay and sketch solutions for county metro transit. So I'll turn it over to you all.
All right, I'm just gonna full screen this for y'all. Go ahead.
Hey everybody, thanks for joining us and thanks to the conference for hosting. So my name is Esther. I'm an associate transportation planner at Nygaard's Portland office. And I've been using R since about 2014. Nygaard is a transportation planning consulting firm, and we have also offices across the United States, but we have an office in Portland and in Seattle.
And hi all, I'm Brian. I'm a data specialist in the Portland office of Nygaard, and I've been using R since I started grad school in 2013. Today we're discussing a tool we developed with R and Shiny to diagnose bus network delay issues and develop sketch solutions. We're presenting the iteration we developed for King County Metro, which is the transit agency in the Seattle metro region, but started developing this tool initially in Portland for TriMet and are now working on another version in Denver.
Okay, so first we're going to talk a little bit about the background motivation for this tool and project, and then summarize the development process and some of the challenges, and talk about the technology stack, and then we'll do a little bit of a demo. So first the background. So buses are the workhorse of transit systems, and being able to diagnose and address delay to improve service is really important to encouraging transit use across the country. Next slide. So buses carry more than half of fixed route ridership in many large urbanized areas, including Seattle and Portland. And as you can see on the graph on the right, the use of buses actually increased as a proportion of all transit trips when COVID hit. So folks that continued consistent use of transit during quarantine are often considered what we would call transit dependent. So it really means that providing quality transit service to them should be one of the highest priorities, and that buses are one of the most vital modes to provide service for people who need it most with transit. Next slide. So despite how important buses are, they are slowing down. From 2009 to 2017, TriMet bus speeds decreased by 9%. So while this was before the pandemic and traffic congestion has generally decreased during the pandemic, car ownership has increased. So we don't know really what to expect over the next months and years, but as people start to return to a more normal routine, we do expect congestion to rise again. Next slide. So for this project, we wanted to analyze reductions in bus speeds across time and space. So we defined a series of metrics related to delay. So we aggregated trips across a time period and compared the 20th percentile travel time to the 80th percentile travel time per trip. Next slide. Yeah, so in this case, really what that means is that we're defining delay for a trip as a difference between a relatively good travel time and a relatively bad travel time for that trip, essentially. So the source data comes from GPS units mounted on buses that track a bus as it travels along its route. So this gets us the travel time information, and then there's also data from automated passenger counters at each bus door that count the ons and offs at every stop. So this gets us information about when a bus is stopping and for how long, and how many people are on the bus, which is referred to as load. Load is important because then we can understand how many people are impacted by the delay. So as you can imagine, this data gets pretty large very quickly, and without tools like R, it's really, really difficult to analyze. And typically, this type of information is analyzed by transit agencies and often at the route level. And while this can do a great job of identifying issues for particular routes, it's tough to really look at the bus service as a network. But because buses are running on the street network and there might be more than one bus using the same road, even if they're using different stops, we need to be able to look at that bus network as a whole and identify those choke points as they relate to the whole network, not to individual routes. So to do that, we developed a custom street segment file that's used to aggregate all of the summary statistics for each route together so that we can look at delay across the whole system, regardless of what route you're on or what stop it's at. And so just to illustrate like the size of that data, the street segment file we created for King County has just over 3,200 segments in it, so it's pretty large. So I'm going to pass it over to Bryan to talk a little bit more about the tool.
Thanks, Esther. So I'm going to talk about the development process of what we've called BDAT, the bus delay analysis tool. And here's a simple sketch of kind of the data pipeline. As Esther talked about, we get a lot of these raw data sheets from transit agencies, from both AVL and APC data sources, and those are united with this custom segment network that we developed. And uniting those two data sources, we're able to show delay and other metrics across routes at the segment level. And I'll zoom into some of the segments in a moment. We decided for some performance reasons related to the Shiny application to create a lot of the charts that we're going to show in the app offline, just as binary files, simply because of the data that is used to make them gets pretty large, and the charts themselves are pretty complicated. And so generating them all offline and then loading them into an S3 bucket to pull on demand into Shiny was actually quicker than trying to like generate them on the fly. You know, we kind of figured that out through experimentation. The other main data source that the Shiny application is pulling is a Postgres SQL database, which lives in Amazon RDS. And that has all the information specific to the segments, as well as a bunch of other metadata. To talk a little bit about the data processing part of the pipeline, we try to stay within the tidyverse where possible. So we use a lot of tidyverse packages, including the ones shown on screen. As far as the geographic data itself, we try to use SF as much as possible. There are a few other geographic packages that we used for certain calculations. Some of the development challenges in the data processing part of this, well, the first one was, as Esther said, was generating the segment geometries. There's some automation we were able to do as just like the first pass, but a lot of it was manual and kind of subjective of like, how do we think transit planners will want to represent this data geographically? And there's a lot of different factors that go into that the computer is not going to understand. So I think there'll always be some element of manualness to this process. The geometry math to map stop pair data to segments is very complex and it just takes a while. So like when I have to run the data processing script, it could take like 12 hours to run. And so when we change something, that's, you know, another 12 hours. And, you know, we definitely had to think about that in our development process. As well as handling multiple route patterns, which is something transit agencies do, especially when they have like a long route and they want to run a short version of it. That can cause challenges for both charting as well as cumulative metric calculation. The web application itself uses a lot more packages. I've grouped them into 4 groups here: the database, and AWS packages, interactivity, spatial data and mapping, and visualizations. And here's some of those packages that we used. I don't have time to go through each one of them. The other thing I want to note is that we developed a lot of custom CSS for the application, just to get beyond the styling that we were able to do in base Shiny. The dashboard itself, some development challenges we encountered there were figuring out how to layer lots of geographic data using Leaflet, and I'll demo one of the performance challenges we ran into there in a moment. Also trade-offs between processing speed and reactivity. As you'll see on the application, there's a lot of knobs and dials that you can manipulate, and we didn't want to have the application respond to each and every single one of them because it would just bog the whole thing down. And so there's some things that are reactive and some things that are not, and you just have to click a button that says calculate. As any software developer knows, trying to accommodate all the different types of user input you're going to see in the application, you know, definitely causes some challenges in how we develop certain pieces of it. And then tweaking the Shiny Apps IO where this is hosted, server settings to make sure if there's multiple instances of this running, people are not having conflicts in data that they're referring to. So now I'm going to demo the application, and I'm gonna have to switch which screen I'm sharing. Okay. All right. So you should be able to see the shiny application. Someone let me know if that's not the case. Okay, so I wanted to quickly go through a couple of the tabs of this application. The main one here is the system-wide tab, and this really shows off the utility of our segment network that we developed. This allows you to see all of the data aggregated to every single segment. So for example, you can see what was the passenger load on that segment, and the delay metrics, what routes were on it, etc. The one thing I did want to show as far as the layering, just to talk about challenges, the demographic underlay layer, which shows census block group level data. So this is population density. Initially, we wanted to just load every single one of these into the leaflet layers. The problem we ran into was with just too much data. And so we ended up using a leaflet proxy to be able to switch which one you're looking at and just like swap it out in a generic demographic underlay layer. The other thing I wanted to show folks was in the route profiles tab. So this tab, even though we definitely emphasize analyzing at the segment level, analyzing at the route level is still important, and it allows us to make some more complicated charts. And so these are most of the charts that I'm talking about that are loaded in kind of from the AWS bucket. So showing load over the course of the route, and the ones I really wanted to show off were these speed and reliability heat maps. And so if you expand this, you can see what the median speed of the bus is at different locations along the route over different times of the day. And so this plot really helps folks figure out quickly, like, where is this particular route slowing down along the route. Okay, and the last thing I wanted to show here was the projects tab. And so the goal of this tab is to be able to quickly sketch out solutions to delay issues. So I'm going to run through a really quick project creation. So we're going to select a few segments on 3rd Ave in downtown Seattle, which folks might know is the transit spine. And we are going to change some stuff about that segment. So here is where you are allowed to set what the directions of the project segments are that you're looking at. In this case, the directions look okay, but if they, for some reason, were swapped just based on how they were drawn, you can correct them so that it's all consistent. So we want this side to be northbound and this side to be southbound, and we can rename our generic direction 1 and direction 2 to that, so they can be referred to as that throughout the rest of the process to make it a little more human readable. And then we can move to adding treatments to those segments. So the first type of treatment we're allowed to add is line style treatments. And one thing we wanted to implement with line style treatments that was interesting was the ability to split segments if they don't exactly align with where your linear treatment is. So if I wanted to break a treatment at Madison Street, but I didn't have a segment break there, I can add one in and select individual segments that I want to comprise a bus lane with. I can select those, and then you can manipulate a bunch of settings. I'm just going to make it really simple. It's going to be a transit only lane, which it already is, but for the sake of demonstrating this project. And I'm going to set that to both directions for that piece. So you can see the direction arrows kind of showing folks what that is. This shows all the segments and the different settings. I'm going to add those to my project. And then I'm going to add one more treatment to show that off, which is manipulating signals. So here you can see existing signals that are along the street. And we're going to take those signals and we're going to make them queue jump signals. Don't worry about what that means. It's a special type of signal that gives priority to transit. And we're going to make those both directions and add those treatments to our project. And then we are able to review the project, and we can see our transit lane that we create, as well as the signals that we can manipulate. One thing I did want to show off was this custom kind of linkage that we developed between the map, where you can select the signals, as well as this data table. So you can see, okay, these are the signals that I highlighted on the map versus the table. If I messed up and I actually don't want one, I can delete it using this custom little trash button we did. So once you're happy with all of your settings, you can give it a name and a description, save it out to the database. And we are actually in the process of developing a tool to then estimate benefits based on the settings that you've developed for your treatments. And with that, I'm going to end the presentation.